It's another, it's Dante, that's D lab number 3. And after this one, I'm going to run lab number 4.
Mr. Pham, Marcelo here. Could you please run my the lab 3, please?
D lab what? Number 3?
Yes, sir. The lab number 3.
I already saw it last time. This one is I just get on the new upload D lab number 3. Which one I ran, I already set it aside, okay? So I just run the one you new upload.
Sorry, I didn't understand. I upload my DLab 3 already.
Yes, you have upload DLab 3 I already ran, and now I will run the that's it, new upload, okay? Any like you upload long times, I ran it already, and now I run the new upload, and I have to save time for another lab. Okay.
Maybe he not see his program been running.
Let me see.
Yeah, you have not run my test, Mr. Pham.
Let me see, Marco.
My name is Marcelo.
Yeah, yes, I see it. I see the lab number 2. Marcelo, the lab number 2. And then let me check and see, is that your the lab number 3 in here? No, I don't have your the lab number 3 as an upload here. I don't know. Let me check and see that you already upload. Okay.
Yes, sir. Thank you.
You are the first one here. Oh. You are the first one here. This is the lab number 3. Okay. Let's open that one and see. Yes. We can run first. Okay, I got your program here, Marcelo. Let's check and see. Okay, let's. Okay, it's good. Let me check. See Marcelo.
Thank you.
You're welcome. Okay, now I'm going to run. I have a couple at D lab number 4. It's just upload it today. Okay, it belongs to, let me see. Oh, Oscar, right? I have it today, so I will run it number 4. You have a lab number 3. It's also uploaded today. So it's already test. So now you will see it, whatever you prepare for the C++ on the D lab, it running with the hardware. Okay, and keep finish your C++ after you're done with the Excel. Complete your C++ and upload. Then I can test it for you. And also, if it makes some simple mistake, I correct it for you. Okay, but you have to upload your lab. So I wait after the spring break now. And if I don't get any more new the lab upload, and then I will make a list of who is missing the lab. Okay, and I put it after it spring break. So I have quite a few the lab number 4. Let's see. Do I have time to run a couple more lap 1 and 2?
How many lap 1 and 2?
D lap 1 and D lap 2. Maybe couple more tests. They just uploaded last couple of days. So I will run it D lap 1. So now D lap number 1. D lap number 1, Marcelo.
Yes, sir.
You need to review your D lap number 1. You see, I just ran it. It failed with more than one test. Okay.
Sorry, could you repeat the last part?
Number 1, D lap 1.
Yeah, it failed on which test?
Okay, now let's see. I run it, and then you make sure you make a note of it. Okay.
Okay.
This one is the individual test, just a single test by test. Oh. Let me check it again. Okay. I connect it again to make sure it's everything okay here. I don't believe it failed, but it already failed. Let's do it again. Okay, it's a Marcelo. It's a failed test 3 and test 8, but this is a simple test, just a single individual test. So I will look at it and then I will correct it for you.
Thank you, Mr. Pham.
Now I have let me see, one more DLF one. It has been uploaded. I download and then at the last time we just run 3 and 4. We not run 1. So now we come back to run 1 and 2. Now let's see. Let me see. Okay, let's run it. I want to run the left number 2. Let's say who else here? The left number 2. This the left number 2 is just upload. Okay. I have a quite a few the left number 2, so we check it out. I have maybe like 3 more left, number 2, and that will be done for today. Okay, so let me run it on of the lab number 2 today. So today we run a lot of lab that most of your lab upload it has been testing and running. Okay. So I know what you want to see how your software working with the hardware by running the test here. Okay, so I try to run as much as I could. Hmm. Oh, this one is the D lab number 3. Let me see, isn't this one D lab number 3? But I put it D lab number 2. Okay, so I will run one more is the lab number 2. That is lab number 3. Okay. Now I have one more the lab number 2 to run. Okay, and that's all for the lab testing tonight. Hmm. Okay, this test, the lab number 3, it's a failed test number 3, but I'm shook again. I will look into this test and then I correct it. Okay, and this is all of the lab testing with the hardware tonight. Mr. Pham.
Okay.
Let me try to unshare it first. Stop share.
Okay, so today we start with the counter. So before we go into the detail, okay, I will let you know how the counter working. Basically, the counter you just counting the number, okay, like you counting 0, 1, 2, 3, 4, 5, 6, 7 to whatever number you want, and we will be using the digital. That means the binary. Okay. If you're counting a number 0 to 3, okay, so the first number is a decimal. 0, 1, 2, 3. And now the binary. 0 will be 0. 1 will be 0, 1. Okay. And 2 and 3. So basically, in the binary, they're using the flip-flop for each bit. So if you're counting in the binary from 0 to 3, how many flip-flop do we need?
Four.
Okay, now one flip-flop, they get only one output cue. So if you get a 0, 0, that will be required 2 flip-flop. Okay? Can you recognize that?
Yes.
Okay, the thing is that, like I can say, Q1 and that will be Q0. So 0, 0, that means both output flip-flop equal 0, 0. 0, 1, that means one flip-flop will be 0, the other one will be 1, and so on. So basically, depending on the number you're counting up to, then you will be need how many flip-flop. I give you example. If I want to count 0, 1, 2, 3, 4, 5, 6, 7. How many flip-flop?
3.
3. The thing is 0 here, you're supposed to get 0, 0, 0. 0, 0, 1. Okay, 1, 2, 3, 4, 5, 6, and 7. So basically, depending on the number, okay, you counting. Now, each number here, we call a state. State 0, 0. State 0, 0, 1. Okay, that will be a state number. Okay, how many states in here?
8.
And on that one, right? For state. However, the decimal, they go up only, either 7 or number 3, not number 8. So if you want to know what the decimal number maximum, decimal, you're using the formula Joule power of n minus 1, where n a number of flip-flop. So if you get only two flip-flop, Joule power of Joule minus 1, you get the maximum will be 3 in the decimal. If you get 3, Joule power of 3 minus 1, and you can get 7. Okay? They get the each state. However, the decimal will be less than 1. Okay? That's why they're coming up with a modular. Modular let's see, modular 8. That means eight state. Okay? And that's a very, very simple thing. We not go into the detail inside the counter. No way. Okay? But we need to know how the counter working by looking into the data. Now, they get the two different type of the counter. The first one is synchronous counter, or they call it ripple counter. Now you can see they get only 2, okay? Only 2 flip-flop, JK. So the modular will be what the modular?
Modular 4.
4. They're telling you they get the 4 state. But the counting will be up to number 3, right? The thing is Joule power of Joule minus 1 is number 3. So now, they're using JK flip-flop to build. with JK tied to high. So when the JK tied to the logic 1, every time they get a transition of the clock, what happened to the output? Remember the truth table for JK. If J equal 1, K equal 1, when they got the clock transition, what Q? Do you remember the truth table for the JK? J and K tied to 1. When they get the clock transition, what happened to the output Q? Nobody know?
Toggles?
Toggle. If you're looking back into the JK truth table, J1, K1, you get a clock, they will be toggle. What that mean for toggle?
It means if the clock was one, or I'm sorry, if Q was 1, it will change to 0 and vice versa.
Right. Toggle mean if it was 0, then they go to 1. If it was 1, then they go to 0. Okay? And now you can see for the asynchronous counter or ripple, the clock go into the first one. But the second one, the clock going from the Q of the first flip-flop. I can say Q0. Okay? Will be the clock for the second one. That's why they call a ripple. If you get one more flip-flop, then the output of the second will be go to the clock of the third one and keep doing the same way. So now, at the beginning, you can see the QA, QB will be a 0. That number 0. And when the clock going high to low, okay, the first one will be toggle. 0, now they go to 1. However, the second one is not. The thing is, Q0 will be go from 0 to 1. Okay, right here. Go to 0 to 1. That's not a transition. So that one, JK will be no change. So that's why QB, they still be 0. And now for the next clock in here, the first one toggle all the time. They toggle the 0. And now from a 1 to 0 will be the clock for the second one. And the second will be toggle. Okay? And they keep doing the same thing. So now they will be count from 0, 1, 2, 3. Okay? Then 0, 1, 2, 3. Okay? They will be go over and over. Now, we see. You get the first one step here, second one here, next one here. This is 0, 0, 0, 1, 1, 0, 1, 1. Okay? Now, they draw this arrow this way. What that mean? That will be telling you, right now we've been in the 0, 0. We don't have any the clock. So that's why they stay in the 0, 0. When they get the clock, they go into number 1. Okay? So that's why they go into number 1. Then the same thing, at the output 0, 1, they can stay to waiting for the clock. And if the clock, they go into next one. And they doing the same way. Okay. Okay, that means how they counter running. They will be 0, 1, 2, 3, 0, 1, 2, 3 forever. Okay. So,
Hey, Mr. Pham, quick question.
yeah,
What does the term steady state mean? Steady state.
that means they stay there doing nothing. 0, 1, that means they stay on 0, 1.
Okay. Okay.
And a synchronous counter is one in which the flip-flop within the counter do not change state at exactly the same time because they do not have a common clock position. This clock coming from here, they not go directly to the second one. So that's why they cannot change the same time. Okay. 2-bit asynchronous counter. Okay. And now you can see, given you that one will be 3-bit. Okay. 3-bit. The first clock go into the first one. Output QA go to the clock of QB. Output QB go to the clock of QC. And you understand me, for 3 flip-flops, they able to count from 0, 1, 2, 3, 4, 5, 6, 7. Okay, then go back to 0. And this is the timing for that, okay? First thing you get a 0, 0, 0. Then next clock you go to 1. Next clock you go to number 2, 3, 4, 5, 6, and 7. Then go back to 0. So you see that's a very, very simple thing. Okay. Now you can get another type, different type. 2-bit synchronous binary counter. On this one here, if they using the JK flip-flop, you can see the clock go to the first one and also go to the second one at the same time. Okay? And the counter will be counting the same way, like the Ripple counter. You get 2 flip-flops, you can count 0, 1, 2, 3, 0, 1, 2, 3. Okay? And if you want to using the D flip-flop, this is the D flip-flop. Okay? Still counting 0 to 3. However, they need to add in inclusive or getting here. Okay? Now, compare between the Ripple counter and the synchronous counter. Which one is better? I can tell you, a synchronous binary counter will be faster the Ripple counter. You know why?
Because you got to go through one extra step.
The thing is the clock going to both flip-flop, so output will be changed the same time. Okay? On the other one, the first flip-flop change, but the second is not changed yet. Okay? So that will be slower. Okay? That's only the difference. However, design for synchronous counter will be more complicated. Easy to design a Ripple counter. Okay? And basically, If you're looking on that one here, what type of the counter?
All the clocks going together, so that's synchronous?
Exactly. This is a synchronous counter. How many bits?
4-bit.
4.
4 bits. You get 4 flip-flop, you get 4 bits.
Mhm.
They can count from 0 to 15 and 0.
Would you call that modular 16 or modular F?
Modular 16. 16 state. Modulus will be a number state from 0.
And is modulus also like the number of tests? The number of tests, is that the same as the modulus?
Yeah, the state will be stacked from 0.
So in other words, like test 1, test 2, test 3, test 4?
Yeah, up to 16.
Okay.
Okay, that's a binary, same thing. We don't care that. What is it here? That's also the synchronous up and down counter. They just give it to you, but the thing is, we will deal with this thing here. Binary counter. Okay, this is a synchronous 4-bit binary counter, and the name will be 74 LS193. If you're looking on a pin layout, this IC will be 16 pins. Okay, pin 16 will be power 5 volt, and pin number 8 will be ground. If you're looking on the pin layout, can you tell me how many flip-flops will be inside this IC?
4.
Or you can see QA means output A, QA, QB, QC, QD. Guarantee you get 4 flip-flop inside. Okay?
Hey, Mr. Pham, since you said 4 bits, so each counter is 1 bit, right?
Right.
Okay, thank you.
Okay, so now see this. You never go into inside of the IC. Only thing is you know how they working. I can telling you how many functions they get. The first function they say clear. That means reset. Output supposed to be 0. Okay? And the second function they will be a load. What that mean load? That means they can loading into the output of the counter, QA, QB, QC, QD, any number you want. For example, you say I've load number 5. Then you can loading to output number 5, and now you can start counting. They can counting 5, 6, 7, 8, 9, 10, go up. You don't have to be counting all the time from 0. Okay? You can count from any number. Loading the number to the output counter, then start counting. Okay? And also this counter, they get another function will be you can counting up. Okay? That means you can counting 0, 1, 2, 3, 4 up to 15. Or you can counting down. That means you can counting from 15, 14, 13, 12, so on. Okay? That means on up that function of this counter. And if you're looking into here, they already telling you, okay, data, input data, okay, pin 10, pin 9, and let's see, pin 1, input B, data B, okay, and 15 data A. So if you want to loading number, okay, number 5, 0, 1, 0, 1, then you apply 0 to A, 1 to B, okay, 0 to C, and 0 to D. Then now you can load, okay? And they get another 2 output. They call a borrow 1, borrow 15, carry out, and borrow out, okay? That output will be active load, okay? That means when they go to 1, they telling the people they already complete for one counting sequence. For example, if the counter counting up 0 to 15, so when the counter reach 15, then pin carry out here, they will be go to high, okay? Then they go low. That let the people know they already done for complete counting up. And the borrow, normally they logic 1. When you're counting from 15 down to 0, when they reach 0, that output 13 will be go high to let the people know they already done, okay, for complete one cycle. You can see this is normally they apply into your watch, okay? That means the first counter they count for second, 0 to 60 seconds. And the next one will be a minute. After 60 seconds, and the second one will be count 60 minutes. And after 60 minutes and the hour, they will be count 1. Okay? So they need that line carry out. Okay? In order to tell the next, if they already done 60 seconds, and the next counter will start counting. Okay? So in the listing here, I say counting up 0 to 15, then to 0. Counting down 15 to 0 to 15. Load any data to the output of the counter. Or you can clear the output to 0. Okay? That is our own function. And when we say this IC working, that means you have to test everything requirement. First thing I need to test for reset clear. Make sure output to be 0. The second thing I have to testing for loading any data. I can verify output will be working, okay? Then I have to testing for counting up, then counting down, okay? Now, in here they say clear active high. They will be higher priority. That means clear will be on pin 14 here. If you apply logic 1, output will be QA, QB, QC, QD will be 0. They set higher priority. That means they override everything. Okay? That means when you clear at the logic 1, and they don't care input for the load, data on the load, counting up or counting down, doesn't matter. The output must be 0. That is the first priority. Okay? Clear equal 1. All output must be 0. Don't care any other inputs. Now the next will be load. Load active load. Second priority. If a load equals 0, then the output Q0 equal A, Q1 equal B, QC, Q2 equal C, Q3 equal D. Okay? Or in this one, you can say QA equal input A, QB equal input B, QC equal input C, QD equal input D. And clear must be 0. That means you don't want clear. If clear equal to 1, load cannot work it. Counting up. First thing requirement, clear must be 0. Load must be 1. Okay? If load is 0, you cannot count. That's the second priority. Okay? And count down. Pin number 4 equal 1. Count down pin number 4 will be equal 1. Positive clock apply to the count up. So this is to make the counting up. Okay, what you need to do. Clear have to be 0. Load have to be 1. Pin 4 must be 1. And you apply the clock to this pin here. Okay, then they are counting up for you. And counting down, same thing. Clear must be 0, load must be 1. Count up pin number 5 now must be logic 1. And the clock apply to count down pin 4 and they start counting down. Now the key point right here, when you add work, you get the IC you not quite understand. You go to Google. Okay? They given you own information. This is what I call a timing diagram for 193 IC. Okay, the first one you can see right here. Clear. Clear equal 1 and you going down. What Q equal?
0.
0. 0. 0. 0. See that? For the clear at logic 1, on the output must be 0. Okay? And the next one, they want to load. So, in order to load, clear must be 0. Okay, now, if the close, that means the data from A, B, C, D will be going to QA, QB, QC, QD. Okay, so let's see what QA equal. If you're looking on that one, what QA?
1.
1, perfect. QB?
0.
1. 1. You know what number? 1101.
13.
13.
D.
Okay, so that's why they say 13 right here. Okay, so in order to load the data from the input to the output, clear must be 0, load must be 0, and the data A, B, C, D, whatever you want, they will be going to the output. In this timing here, they load number 13, 1101, so the output will be number 13. Okay, 1, 1, 0, 1. Okay, that is a function for the clear and a function for the load. Now they start counting up. When they counting up, you see right here, the clock here. See that? Clock for counting up. So clear preset must be 0. Load must be 1. They must be. Okay? When the clock coming, okay? So clock will be going from 0 to 1. Okay? 0 to 1. Let's see what the number here. Output here will be 1, 0. No. Okay.
That's before the first positive clock transition, so that's still 13 there.
Exactly. Okay, clock going high to 0. 0 to 1. Right here. That is the clock. So the clock, after the clock, that will be 0. That will be 1. That will be 1. That will be 1. What number?
14.
You understand that they load number 13 already. When they start counting, they will be go to 40. Okay? That's why they go to 40. Now, then next clock, they will be go to what number? 1,
15.
1, 1, and 1. 50. Okay? And after the 15, they go to number
0.
0. Okay? That means they go from 1 to 15, then go to 0. Keep going forever. However, by the way, carry out. You can see there's a carry out here. Carry out normally logic 1. When they go low,
It goes low when the count reaches 15.
exactly. You can see right here. They go low when you get a 1, 1, 1, 1. Let the people know I already reached the maximum. Okay? Then go to the next one. They will be counting down. Counting down here. Now you see the clock will be go into the pin counting down. Okay? That will be the transition right here. Okay? So after you get the 0, let's see. Right now, they get let's see what number here. 1, 0, 0, 0. Number 1. Okay? That means number 1, when they get the clock, they count down. They will be count to number 0. Okay? And after number 0, count down.
Mr. Pham, I have a question.
Yeah.
When counting down the first number, you said it's 1.
Uh-huh.
So the top 1 is the least significant bit. How it's count? 0, 0, 0, 1 or 1, 0, 0, 0?
You have to see Q. QD. Most significant bit. You have to count from 0, 0, 0, 1. That means 0, 0, 0, 1. Okay?
Yeah.
QD,
Uh-huh.
QD means this is the mode.
Okay, thank you. I got it. Thank you.
So if you on a number 1 and they apply the clock for counting down, they will be counting down to 0. Right? We going down. You are already at the logic 1. Count down, they apply the clock, you go to 0. Now if you 0, you apply the clock, they will be count to 15. Not 1, okay? If they count to 1, means they count up. Now they count down. Okay?
Uncover that up. You covered it up.
Yeah. So 0, 0, okay? 0. Then That telling you how come? Let's see. I don't want that one. Okay. Now, if you counting down to 0 and you apply the clock, they go to 50. 1, 1, 1, 1. And if you apply another clock, they go to 40. Okay, you can see here. 0, go 15, go to 14, 13, and so on. Now, we're looking for the borrow output here. Normally, they logic on 1. When they go low.
When the count reaches 0.
Exactly. When the counter going to 0, they go low for short time. Then they go back to the 1. Just let the people know I already reached 0. Okay? So that is the timing diagram. You looking into that, you're able to tell what logic on the signal supposed to be. Okay? For clear, or for the load, or for the count up, or for the counting down. Now, on this IC here, 74192, they call a BCD counter. Okay? What does BCD stand for?
Binary coded decimal.
Binary code
Coded decimal. Binary coded decimal.
decimal. Now, what that means? That's telling you they working like the decimal. Okay? But they are binary. They working like the decimal. So the same thing in the decimal, you don't have a number 10. Decimal will be 0 to 9. Okay? So BCD counter, same thing. They will be counting from 0 to 9 and go back to 0. They cannot go more than 9. If you're looking into the pin layout, Q1, Q0, okay, Q2, Q3. They get the 3 output. And I know inside they get a 4 in output. I know inside they get a 4 flip-flop. Okay? Normally for flip-flop, you can count up to 15. However, this is a BCD counter. They only count up to number 9. Okay? And the function will be identical into the other one. Binary counter 193. Okay? That means this counter can counting up 0 to 9, counting down 9 to 0. They can clear pin 14. MR means master clear. Clear the output to be 0. Or they can be load any number. Okay? From the input, you can see they get a P2, P3, P1, okay, P0 input, and you can get a PL load identical to the other one. Only thing is the difference will be One can count 0 to 15. The other will be counting only 0 to 9 or 9 to 0. Okay, so normally you can see you get a 74, 191, 193, 1, okay, 61, 163. So that will be a binary counter. And also you can get 74, 192, okay, and 74, 160, 74, 162. BCD. So normally they doing this way. Odd number is for binary. Even number using for BCD counter. Okay, now I want to say you, if you're looking on the two table, select table here, for the first one here, that means they want to test for master reset. MR means master reset. So to test for MR at a logical what? How about PL, CPU, CPD?
Don't matter.
What happened?
They don't matter.
Don't care. Right?
Right.
Admin don't care. Now, admin don't care. That will be for your guy to do your job. When you apply MR equal logic 1, you want the output must be reset. Output have to be on 0. So now, if the output is not 0, what can you do?
You have to check pin 14 to make sure it's at a state 1.
That means it must be check MR, right?
Right.
At logical 1. What else?
That should be it because it's a overriding input, right? So nothing else.
Perfect. That means you know how to troubleshoot it. You check pin MR at the logic 1 and the output is not 0, then change the IC. You cannot say you want to go to check a PL or CPU or CPD. The thing is that telling you you don't care. Can you follow it? That means you learn the technique how to troubleshoot it, how to fix the problem. Okay? And now, the next one they want to test for PL. In order to test for the parallel load, MR must be
Low.
Must be low. And the other one you don't care. So when you load number 5, you're supposed to get number 5. Okay? If you not get number 5, then the first thing you have to say, okay, P1 here, what logic you want, P0 here, P2 here, P3 here. That means you have to take the input there. For example, you want number 5, 0101. Make sure input you get a 0101. Then you have to check the MR, they must be 0. And you have to check the PL, they must be 0. If you get everything in the output not equal into the input, then the IC. You not take CPU. You not take the CPD. The thing is parallel load, second priority. They override the clock signal. Okay. And if you're reading this line here, can you tell me how much you understand? MR low, PL high, CPU high, CPD high. Output they say what?
No change.
No change. Right? They output they say no change. What that mean to you?
It means the output stays the same as it was on
Perfectly.
previously.
That means if the output at that time they number 50101, then now they still be 0101. That means no change. And then you need to counting up, okay, counting down. That have to be low. Load must be high. Clock will be CPU will be 0 to 1 transition. And CPD must be high. Then the counter will be counting. That means on the truth table, they're telling you everything to make it work. So I hope, I will be upload very soon. The counter, okay? And first time I try to get a less happy to see how many students can follow the data into the make the circuit working. Okay, I want to go to this one, 191. You can see you can get 191 for binary and 192 for BCD. The lab will be working on this one first. Okay, you will be working on 191 and also you can working on 192. 191, they say load active low. They don't have any reset on this IC. They get a load. You can load like the other IC, loading any number you want. If load equals 0, QA equals A, QB, B, QC, C, QD, D. Counting up 0, 15 to 0. To counting up, load equals 1. Enable, G equals 0. Now up pin number 5 must be 0. Positive clock up to apply to pin 40. Okay, counting down. Load equal 1. Down up now equal logic 1. Positive clock 40. Okay, so on this one, they get a one input they call up, down, right here. They're telling you 0, they want count up, 1, they want count down. Okay, and then maximum, minimum output, maximum, that right here. Active high, okay. Output active high, normal at a logic 0, and will be high when the Q0, Q1, Q2, Q3 equal 1, 1, 1, 1. Okay. Ripple. RCO output. Okay. Active low. Normal at logic high. And will be low when Q0, 1, 2, 3 equal 1, 1, 1 or 0. Okay, let's see. This is the timing for 191. Okay, and you can looking into that in order to make your test. Okay, if you loading, it is loading here, and you can see what A, B, C, D, then what will be QA, QB, QC, QD. Okay, then now the clock here counting up. Okay, so you want to counting up, then load must be 1. Okay, and the clock here will be 14 here. Will be clock here. Let's see, they get a bubble or not. The clock 14. Okay, positive. Okay, so the clock will be 0 to 1. So let's see. This number here will be 1, 0, 0, 1. No, that's a 1, 1. Sorry, I'm wrong. That will be 1, 1, 1. That's why 50. Okay, and before that, so they get the clock going here. You get 0, 1, 1, 1. That means you get number 14. When you apply the clock next transition here, you go to 15. And after 15, apply the clock, they go to 0. Okay? And now, this is two output is different. Max minimum, they will be go high when the output on 1 and the output RCO carry out. They will be going low when on of the output equal to 1. Okay? And that for count up, and this will be counting down. So we will be get the test for 191 first. Only thing is right now try to reading go through the 191.
Mr. Pham, go back just real quick.
Just a minute. And go to the timing to see, find out how they're working. Yeah. Go ahead, Mr. Smith.
I got it. Go ahead.
Okay. So
Yeah, go ahead. Go ahead. Go ahead.
you will be soon get the lab for the testing 191. Okay. But I said you're looking on the counter for 191. Then you're looking for the timing here in order you can do your lab. Okay. Normally on the test program, okay, I will be giving you one test. Okay, test number 1, and the rest you will be doing. Okay, so now you can see this a little more test. Okay, you want to counting up 0 to 15, 16, 10, and you want counting down 15 to 0 to go back to 15, another 16, 10. That means you already get 32 10. Okay, adding to the other one, they can go to about 40 10. If we try to run the test with the hardware for your guide, we pick only one test program to run. The thing is now of time. Okay. Next meeting.
Mr. Pham, just real quick before you cover that, you know, on your loads, on sometimes, like on some D-Labs you give, you have to put a positive or negative clock, say like with the JK or the D flip-flop. But on this one here, it looks like the clock starts a teeny bit where the load is at. If you look at that dash line.
Now, this is loading override the clock.
Yeah.
Okay, you can get another IC that will be everything controlled by the clock.
Right.
Okay, but not on this guy.
Hmm.
Okay, so
Now I was just looking at the dash line on the data sheet.
yeah, everything will be shown on the data. Okay, same thing at working, you get some IC you cannot understand. Then you can go to Google and get the data. You can look into how many pin, the two table, how they working. Okay. Next time we will be start with I think you guys see blood on the function. Okay. That means at least everyone knows the software, then you have to know about the function. You have to break the whole that program into the small one to easy follow it, easy to make a correction. Okay, we don't want to make a program from the top to the bottom, everything. When you're looking for something, it is really hard to fix it. Okay, and also we'll be using the loop in the C++. Otherwise, later on you can get 512 tests. You cannot sit down and type 512 or over 1,000 tests. No way. That's why you have to learn how to using the loop for, I equal 1 to 1,000. Then you can coding just few lines, but they will be done 1,000 tests. Okay, that next meeting will we go into that. The thing is, after the counter here, and you can get into some different, like, decoder, encoder, multiplexer, okay, anything that's just the IC. Try to understand how they work, how the application in a digital circuitry. Then we go to the memory, okay, and you can understand what's going on inside your computer with the memory. Then the last one will be that ADDA converter. That means your voice, when you're talking in your cell phone, okay, that will be a sound wave. Okay, when they go to your phone, they're converting into electrical, okay, electrical wave. And when they go to the computer cannot deal with the voice. That means analog signal. Then you have to get what they call A to D converter. They're converting your voice into the binary and go to the computer for processing. After they're done, they have to send out your voice, but they have to send in binary. Then now you need another IC. They call a D to A converter. That means now they're converting digital back into the analog and for transmission. Okay, so that normally that apply into your phone. Okay, the cell phone. Okay, any question? So far, I saw you guys doing the lab 1, 2, 3 to 4. That's okay. It's good. You know how to do 1. The way how to get into the visual, you edit your program, compile and run. That means later on will be very, very simple to do the lab. Okay. A main thing on this tech tool will be the digital lab. You don't have too much assignment. Okay. Okay, any question, anything else?
Mr. Pham, I have two basic questions.
Yeah,
The first one, the most significant bit here is QD, right?
the mode QD.
Most significant bit. Okay. And the other basic question is to set the number 13, I have to put in the data inputs. This means A, B, C, D. The combination such D is 1, C is high, B is low, and A is high, right?
1101.
1101. Okay.
What number?
13. When
Okay, correct.
load, when we set this, that is the way to set to this circuit start counting up, for instance, from 13, right?
Right.
Okay, thank you.
That's only telling you you can load any number you want.
Got it. Yeah, got it.
But make sure normally the way they using, okay, for forward, then D have to be the most, A have to be the least.
Okay, got it.
Okay,
Thank you.
yeah. So make sure next week we don't have a class, okay?
Are you going to upload the video this night, Mr. Pham?
Upload what?
The video recording.
I will.
Thank you.
Okay,
Thank you, Mr. Pham.
okay, will be good night, everyone.
Thank you.